Right.
So, wait a minute. Great. So, thank you for everyone coming here for this great conference, and it is truly my privilege to have this opportunity and introduce some of our results and our research in the past 3 years focused on UV technology, especially Far-UVC technology for pathogen disinfection in different settings. So first, I would like to introduce our research team. So in the past 3 years, our research team have been focused a lot on using UVC technology for public space sanitization. And it has been a collaborative research effort between our team at the University of Colorado Boulder, led by Dr. Carl Linden, as well as Dr. Chuck Gerber's group at the University of Arizona, and also Dr. Mark Sopsey at the University of North Carolina at Chapel Hills. So in addition, we also work very closely with our industry partners, including Ushio, Alconsense, Eden Park, Freestyle Partners, Far-UV Technologies, Space Needle, Exmer, and Boeing Company in Seattle. So I would like to take this as an opportunity to really thank them for their technical and financial support, as well as their effort and insight on promoting UVC technology for public space sanitization. And at the end, I would like to thank our funding agency, the National Science Foundation, for their support to our research here. So a little bit introduction on germicidal UV irradiation. So germicidal UV irradiation between 200 to 320 nanometer have been proven to be very effective to fight all kinds of viruses and bacteria in different settings, including water, air, and on surfaces, due to its capability of causing nucleic acid damage as well as protein damage. So in order to do such damages, the UV irradiation needs to be absorbed by the protein and nucleic acid molecules, and the absorption by the protein and the nucleic acid varies with wavelengths, as this plot showing here, which means that the UV irradiation at different wavelengths may have very different disinfection performance. So the most conventional UV devices in the world right now is still the mercury vapor lamp emitting at 254 nanometer. However, the emerging UV technologies such as the krypton chloride lamp emitting at 222 nanometer and germicidal UV LEDs are gaining more popularity due to many of their good features, including small size, wavelength selectivity, and high energy intensity. So there are many configurations using conventional UV devices, such as the mercury vapor lamp, for sanitization purposes, including a UV cabinet, the portable UV sanitizers, the upper and the lower room sanitizers for upper air and floor disinfection, as well as UV for HVAC systems. So although all these configurations have been proven to be very effective for air and surface disinfection, there's one major limitation of all these configurations using the conventional UV devices, and that is all these configurations cannot be used for direct human exposure due to UV adverse health effect. So it means that we cannot really apply all this configuration in public occupied spaces where the most pathogen transmission occurs. So a little bit background on the health effect of UV irradiation. So UV irradiation can cause erythema and photokeratitis, which damage the human skin and human eye cells. So in order to do such damages, the UV irradiation need to penetrate through the outer layer of the dead cell of the skin or the tear layer of the eye and really get to the germinative layer of the cells. So the conventional UV devices emitted at 254 nanometer is capable of such penetration. However, the emerging UV technologies such as the krypton chloride lamp emitting at 222 nanometer cannot penetrate through the outer layer of the dead cells or the tear layer of the eye, which means that this specific UV wavelength is potentially safe for direct human exposure. So this plot here shows the threshold limit value, or TLV, of daily UV exposure without acute adverse health effect. And as we can see here, At 222 nanometer, the TLV value is about 25 higher for the human eye exposure and 45 times higher for the human skin exposure, meaning that the specific wavelength is very safe for direct human exposure. So in today's presentation, I would like to share and discuss some of our results in the past 3 years, focus on using UVC technology for public space sanitization. And the first part I would like to focus on will be on UV activation kinetics of common pathogens. So to determine the UV activation kinetics, we normally use what we call the common beam apparatus, which the output of a UV device is vertically directed onto the test microorganism that normally suspended in a buffer solution. So the goal of the common beam apparatus here is that we can precisely determine the comparative UV activation kinetics of relevant pathogens under a well-accepted protocol. So in our study here, we selected a total of 5 different UVC technologies, including an unfiltered krypton chloride thermal lamp emitting primarily at 222 nanometer with a second peak at around 258 nanometer. A filtered krypton chloride thermal lamp with a bandpass filter that only emits at around 222 nanometer, a low pressure mercury vapor lamp emitting at around 254 nanometer, as well as 2 germicidal UV IODs emitting at 270, as well as 282 nanometers. As for the test microorganisms, we have selected a total of 10 common pathogens that we can find in different settings, including respiratory viruses such as SARS-CoV-2, human coronavirus 229E, as well as influenza, the bacteria that can cause healthcare-associated infections, including E. coli, Staphylococcus, and MRSA, the waterborne bacteria, including Legionella and Mycobacteria, as well as foodborne pathogens, including Listeria and Salmonella. In addition, we also select the 4 bacteriophage and viruses that could potentially serve as UV testing surrogate, including 2 enveloped viruses, such as bacteriophage V6 and marine hepatitis virus MHV, as well as 2 non-enveloped viruses, including MS2 and T1UV. So the key of a standard UV testing method is that we can accurately determine the actual UV irradiance that apply to the pathogen for disinfection purpose. And to do such calculation, first, normally the incident UV irradiance at the center of the sample surface was measured. And in addition to that, 4 different correction factors were applied into the calculation to account for all these different types of interference that happening within this matrix. The first factor we include is what we call the Petri factor, which corrects for the UV irradiance variation across the sample surface. The second factor here is the water factor, which corrects for the UV irradiance reduction across the sample depth due to the UV absorption by the sample matrix. The third factor here is the divergence factor, which also corrects for the UV irradiance reduction across the sample depth, but this time is due to the UV beam divergence as the UV irradiance decreases with the traveling distance following the inverse square law here. And the last factor here is the reflection factor, which corrects for the UV irradiance reduction due to the UV reflection at the water-air intersurface. And this plot here shows the reflection value across the UV wavelengths. And as we can see, there's a slight reduction of the reflection value across wavelengths. So combining the incident UV irradiance measurement and all 4 correction factors, we can calculate the average UV irradiance, which represent the actual UV irradiance that directly apply to the pathogen for disinfection purposes as a product of the incident UV irradiance and all 4 correction factors as I'm listing here. So another part of the UV activation kinetics is that we have to determine the UV activation efficacy. And to do that, first for the quantification, we use very standard method for quantifying bacterial cells using the standard plate counting method, as well as using a plague assay for bacteriophage, and also infectivity assay for viruses that requires mammalian cell as their host cell. So after the quantification, we can calculate what we call the log reduction value, or LRV, to represent the UV activation efficacy by comparing the concentration of the pathogens in the sample without and after UV exposure. As for the kinetics curve, we normally use what we call the dose response curve to represent the UV activation kinetics, which the x-axis here is normally the average UV dose, and the y-axis here is log reduction value representing the UV activation efficacy. So for viruses in aqueous solution, the kinetics model is normally following what we call a pseudo first order kinetics model, which is basically a linear curve in the dose response curve. And from this curve, we can actually calculate the K value, which is the inactivation rate constant, as the slope of the inactivation curve here. For bacteria, the UV activation kinetics normally follow a second order polynomial model with an initial lag phase, as I'm showing here. So let's talk about some results. So the entire work started in early 2020, right after the pandemic started. So naturally, our very first thing that we're very interested in is how effective of different UVC technologies to fight against SARS-CoV-2. And here shows the UV activation kinetics of SARS-CoV-2. So as we can see here, so all 5 selected UVC technologies can very effectively inactivate SARS-CoV-2, achieving 99.9% of inactivation with less than 6 μg/cm of the UV dose. And when we compare different UVC technologies, we can find that the krypton peroxymer lamp actually exhibit the best disinfection performance. And this is very promising because not only this device provided the best inactivation performance, this is the device that we think is potentially safe for direct human exposure, meaning that we could use this krypton peroxymer lamp in occupied public spaces to help us control the SARS-CoV-2 transmission during the pandemic. So the next thing we're also very interested in, and is also in urgent need, is to find a proper UV testing surrogate of SARS-CoV-2. So SARS-CoV-2, as most of you know, is a biosafety level 3 pathogen, which means that it is very difficult to do any experiment using this pathogen due to the safety requirement. So here we select the 3 potential UV testing surrogate of SARS-CoV-2, including the marine hepatitis virus, MHV, and also the human coronavirus 229E. Both of them are biosafety level 2 coronaviruses that have very similar molecular structure compared to SARS-CoV-2, as well as very similar genome size here. Another potential surrogate that was selected is the bacteriophage V6, which is different in terms of molecular structure compared to SARS-CoV-2, but it requires a lower biosafety level, which only requires BSL-1 facility to handle this specific bacteriophage. So the result I'm showing here is the inactivation rate constant of the K value that of the 3 potential UV testing surrogate of SARS-CoV-2, as well as SARS-CoV-2, using all 5 different UVC devices that were selected in this investigation. And as we can see here, the marine hepatitis virus MHV actually showing very similar K value compared to SARS-CoV-2 for all 5 UVC devices that were selected in this investigation, suggesting that MHV can serve as a really reliable surrogate of SARS-CoV-2 across germicidal UV valences. The human coronavirus 229E here shows a slightly lower K value compared to SARS-CoV-2 for most of the tested UV devices here, but considering it's very similar to SARS-CoV-2, you can still use the human coronavirus 229E as a proper UV testing surrogate of SARS-CoV-2. the bacterial Far-UVC here shows a much lower K value compared to SARS-CoV-2 for all the tested UV devices, but considering it only requires BSL-1 facility to handle, you could still use as a conservative surrogate if only the BSL-1 facility can be accessed for your study. So, because the 222 nanometer, the krypton coaxial lamp is very promising due to its great disinfection performance as well as its safety, we're also looking into the 222 nanometer UV activation of all other common pathogens that we can find in different settings. So here shows the result of 222 nanometer UV activation of common viruses that we can find. So as we can see here, the 222 nanometer UV radiation is very effective for virus disinfection, achieving 99.9% of inactivation with less than 4 mg per square centimeter of UV dose. And when we compare the inactivation kinetics to the potential UV testing surrogate of viruses, we find that the T1 UV actually exhibit very similar UV activation kinetics compared to all these common viruses, meaning that the T1 UV could serve as a reliable and good representative UV testing surrogate at 222 nanometer. The other two potential surrogates, the bacterial Far-UVC and MS2 here, shows a much lower UV activation kinetics. As for bacteria, so we find that the 222 nanometer UV radiation is also very effective for bacterial disinfection, achieving 99.9% of inactivation with less than 15 milligrams per square centimeter of the UV dose, with one outlier here, which is the mycobacteria, shows a much lower inactivation kinetics. So another thing we're interested in is how the UV activation kinetics at 222 nanometer compared to the conventional 254 nanometer. And here shows the result of UV dose required for 99.9% of inactivation using the krypton coaxial lamp as well as the low pressure lamp. And as we can see here, for viruses, the krypton coaxial lamp is actually exhibiting a much better disinfection performance compared to the conventional low pressure lamp, which only requires half of the UV dose to achieve the same 99.9% of inactivation. But when we compare for the viruses, we find that the krypton coaxial lamp is not as effective compared to the low pressure lamp, which requires about 90% more of the UV dose to achieve the same 99.9% of inactivation. So that brings up the question that why the disinfection performance at different wavelengths shows very different results. And to better explain that, we also look into the genome damage as well as the protein damage that caused by the UV radiation at 222 nanometer as well as 251 nanometer. And here shows the result of the viral RNA damage induced by the UV radiation at these two wavelengths. And as we can see here, the krypton coaxial lamp emitting at 222 nanometer actually caused more viral RNA damage as well as more protein damage, which likely explains that why the 222 nanometer UV radiation actually shows better virus disinfection performance. As for bacteria, our group is currently investigating the bacterial DNA damage, protein damage, as well as potential damage repair mechanism at different wavelengths. So to summarize the first part of my result, we find that the UV activation, so our selected UV devices can very effectively inactivate all kinds of common pathogens that we can find in different settings. So including respiratory viruses, the waterborne pathogens, the foodborne pathogens, as well as pathogens that are associated with healthcare associated infections. The second, what we find here is that based on our SARS-CoV-2 study, we find that the mouse coronavirus MHV actually can serve as a really reliable surrogate of SARS-CoV-2 with a lower biosafety level requirement across germicidal UV wavelengths. And in addition, we find that the T1 UV could also serve as a good surrogate at 222 nanometer, but we need to consider that the T1 UV actually have a very different molecular structure compared to the coronaviruses here. And the third part is that when we compare the disinfection performance at 222 nanometer versus 252 nanometer, we find that the 222 nanometer actually exhibit better virus disinfection performance, but for bacteria, the 222 nanometer is not as effective as 254 nanometer. So the second part I would like to discuss today will focus on UV disinfection on surfaces. So to determine the UV activation on surfaces, first, the solutions with test microorganisms were sprayed onto the surface coupon in an amber spray bottle. And then before and right after the solution deposition, each coupon was weighted, and the weight difference here was used to represent the virus or bacterial load onto the surface coupon. And then our surface coupon were dried under a laminar flow for an hour, and then moved to a column beam apparatus for UV exposure here. So after the UV exposure, the coupons without and after UV exposure were extracted into 1 ml PBS with 0.01% to an 80 by swapping the entire surface 3 times, and then the extracted samples were quantified using standard method here. So after quantification, we can calculate the log reduction value by comparing the concentration of the pathogens in the extracted samples without and after UV exposure, normalized by the virus or bacterial load, as I'm showing here. And then when we look at the UV activation kinetics, we find that the UV dose response curve for surface disinfection is normally look like this. To better interpret this curve here, we decided to divide this curve into 2 regions. The first region is the inactivation region. And within this region, the log reduction value actually increased linearly with UV dose. And then once the UV dose reached to a certain level, we find that the inactivation will actually reach to a second region, which is the plateau region. And within this region, the log reduction value doesn't change with UV dose. And combining these 2 regions, we can use an equation like this to represent the entire UV dose response curve, with the K value here is the inactivation rate constant value calculated from the inactivation region. And the R value here represents the fraction of bacterial viruses that are resistant to UV irradiation, which can be calculated from the plateau region here. So there are 2 major factors that we think that could potentially affect the UV activation kinetics. The first factor is the UV absorption by the dry deposition solution on the surface, which may physically protect the test microorganism on the surface from UV irradiation. And the second factor here is the UV refraction from the surface, which may actually be beneficial for the surface disinfection, as it may cause the test organism exposed under the UV irradiation twice, once from the UV source, and the other is from the reflected UV irradiation from the surface. So to investigate the first factor here, we look into the UV activation kinetics using solutions with different absorbance. So here, use MS2 as an example. So the deposition solution we select here have the absorbance range from 0.6 to 63 at 222 nanometer. And here shows the result of inactivation of MS2 on surfaces using the krypton core lab. And as we can see here, the inactivation actually can significantly affected by the solution absorbance. And we see that the UV dose response curve actually decreases with the solution absorbance, which is what we expected because of the physical shielding factor here. And when we look into the kinetics factors, we find that both the K value and the R value represent the fraction of MS2 that resistant to UV radiation. Both factors here can be significantly affected by the solution absorbance, which the K value decreases with the solution absorbance, as well as the R value increases with the solution absorbance. So we also tested the inactivation of MS2 using different, okay. I'll try to finish. Yeah, that's embarrassing. Anyway, so we're also linking to the inactivation kinetics using the low pressure lamp, and we find very similar result. But it seems like the effect of the solution absorbance is less for low pressure lamp, as most of the inactivation reach to a maximal log reduction value of 2, which equals to 99% of the maximum inactivation. So we also find a very similar inactivation phenomena when we test the inactivation of E. coli on surfaces using the krypton chloroaxamar lamp as well as the low pressure lamp. And we find that for both devices here, the solution absorbance can significantly affect the UV activation kinetics. So, because the importance of the solution absorbance for surface disinfection, when we compare the low pressure lamp versus the axamer lamp, we need to test that with a real case scenario solution absorbance. And here we selected the solution absorbance at 10 per centimeter, which is very similar to the human saliva absorbance at 222 nanometer as well as 254 nanometer. And to summarize this result here, this is what we observe. First, we find that the activation for viruses on surfaces is slightly different for the krypton chloroaxamar lamp as well as the low pressure lamp. And we find that the low pressure lamp is actually exhibiting better surface disinfection performance of viruses. And we compare this inactivation result to the inactivation result in aqueous solutions by suspending the same viruses in the same deposition solution. We find that at 222 nanometer, the viruses is more sensitive to UV radiation in aqueous solution, but at 254 nanometer, we find that the viruses is more sensitive to UV radiation on surfaces. In addition, we also tested UV activation of bacteria on surfaces, and we find that, first we find the low pressure lamp still exhibiting slightly better disinfection performance for both bacteria that we tested here. And when we compare the inactivation on surfaces versus in aqueous solution, we find that the viruses are more sensitive on surfaces compared to in aqueous solution, which is really promising in the way that it basically suggests that UV technology is a very powerful tool to fight against bacteria on surfaces. And another factor, as I mentioned, is that the surface reflection may also affect the UV activation kinetics. And when we look into the surface reflection value of all these common materials, what we find is that a lot of material can actually reflect UV and radiation, especially for metals, tend to have a better reflection value here. The maximum we can observe here is for the alumina, which reached to 60% of the UV reflection. And the reflection could be beneficial for surface disinfection because it can expose the viruses twice, or pathogens twice on surfaces, both directly from the UV source as well as from the reflection from the surface. To summarize this result, first we find that both krypton chloroaxamar lamp as well as the low pressure lamp can be very effective for surface disinfection. And when we compare these two devices, we find that the krypton chloroaxamar lamp actually have a slightly better disinfection performance on surfaces. And when we compare the surface disinfection to the disinfection performance in aqueous solution, we find that the viruses on surfaces are less sensitive to 222 nanometer UV radiation, but more sensitive to 254 nanometer. Whereas bacteria is more sensitive on surfaces in general. And when we test the two factors that can potentially affect the UV radiation, we find that the UV absorption by the dried solution deposition solution can significantly affect the UV disinfection performance on surfaces. And for surfaces, we think there may be a potential beneficial effect of the surface reflection for UV surface disinfection here. So with that, I would like to just 1 minute. So yes, sure. So I think that based on our result, we think that UVC technology, especially the Far-UVC technology, should be an ideal solution for public space sanitization that is very safe and effective for both virus and bacterial disinfection, so that in the next pandemic, we don't have to rely on masks to protect us from the pathogen transmission in public spaces, especially for high-risk spaces like public toilet, healthcare facilities, schools, and buses. And as for the future research need, I think we need to have a fairly robust and reliable standard testing procedure to validate the UV device performance, as well as we also need more research on understanding the safety and health effect of UV radiation for direct human exposure. And finally, we need more effort on UV device design optimization and application. That will be all for my presentation. Thank you.
Okay, any question, quick question I can allow?
Yes.
One, because you run out of time.
You find me after the break session if you have questions. Yes.
Hi, Ben. Great presentation you've got here. I was wondering, so you said you hypothesized that there was a plateau that was reached for UV disinfection on surfaces, but some of your data didn't necessarily seem to showcase that. Would you say that that's because you had the wrong mathematical model, or maybe that you didn't have the right fit and that it would extend further but would eventually reach a plateau? Do you have an idea about that?
Yes, so we actually, that's not the only mathematical model we try. So we actually try 2-region linear model, which we don't really have a plateau region. So basically the first region is the quick rapid inactivation, and the second region is the slow inactivation. And yes, for some of the results we find that model actually fits better. So we are still looking to whether or not eventually we'll reach to the plateau region. That is question, but my hypothesis is that for a lot of real case scenario surface disinfection, we may reach to a plateau region simply because there are a lot of things that within the matrix on the surfaces that can block UV, and you may always have a dark spot on the surface that the UV irradiation simply cannot reach to there. But yes.
Okay, so